Welcome back to the deep dive. We're here again to unpack complex topics, pulling out the key technical insights from the research papers you share with us. Today, we're plunging into the world of machine translation. Specifically, we're looking at how researchers are trying to make large language models, LLMs, much better at it. We're zeroing in on a really interesting new method for picking the best data to train these models. It's all laid out in a research paper titled CRPO, Confidence Reward Driven Preference Optimization for Machine Translation.
That's right. And as always on Neural Intel, our mission here is purely technical. We want to extract the core insights from this CRPO paper, really get our heads around the mechanics of their proposed method, and see how it stacks up against what's already out there. Strictly focusing on the technical details and what they mean for, well, how we might approach training these models going forward.
Okay, sounds good. Let's set the stage then. LLMs, they've obviously revolutionized so much in NLP, right? But machine translation, MT, it still feels like one of those areas where they face some unique hurdles. Is that fair to say?
Oh, absolutely. It definitely is. And a big part of that challenge, it really comes down to their pre-training. I mean, these models are trained on absolutely massive data sets, huge chunks of the internet, basically. And historically, that data has a pretty significant English-centric bias. So while they learn amazing general language stuff, this bias means they don't just automatically nail translation between, say, dozens of languages straight out of the box.
Right.
It gets particularly tricky for languages that aren't as common online, or when you're dealing with really subtle linguistic nuances, things that are maybe quite far from the English structure they saw so much of during pre-training.
So even after all that huge pre-training effort, there's still this gap. You need something more to make them truly effective multilingual translators. What was the first approach researchers took to, bridge that gap?
Well, a pretty common initial step was something called instruction tuning. The basic idea was you take your massive pre-trained LLM and you fine-tune it a bit more. But this time, you use diverse multilingual data sets, and you pair them with specific instructions, like explicitly telling the model, translate this German sentence into French, or here's English, give me the Arabic.
Uh-huh.
The goal was really to expose the model to a wider variety of languages, sure, but also to the specific format of a translation request. You're trying to boost both the range of languages it handles and the actual quality of the translations it puts out. We saw quite a bit of work in this space exploring instruction tuning for multilingual LLMs.
Okay, that makes sense as a starting point. But it sounds like instruction tuning, while probably helpful, didn't quite get these general-purpose LLMs all the way there. They still maybe lagged behind those specialized, purpose-built translation models we've had for years, like the strong encoder-decoder types.
Exactly. Yeah, there was often still a noticeable performance difference at delta. And that gap pushed researchers to look towards more, let's say, advanced alignment techniques. They started drawing inspiration from successes they were seeing in other LLM applications. And reinforcement learning from human feedback, or RLHF, quickly became a very attractive option. The idea was to align the LLM's translation outputs more closely with what humans actually prefer in terms of translation quality.
RLHF, yeah, that's a term anyone working with LLMs now knows very well, especially for things like making chatbots more helpful or, less likely to say something problematic. How does it work specifically for machine translation, though? Is it the same basic process?
The core mechanics are pretty similar, yeah. The first big step is you need to build a reward model. This is typically a separate neural network, and you train it on a data set of human preferences. So imagine for a given source sentence, you have maybe 5 different machine translations. You'd have humans rank those translations or maybe pick the best one or compare pairs. The reward model learns to predict those human preference scores.
Okay, right. So the reward model is essentially learning this function that tries to mimic a human judge, saying, okay, this translation looks better than that one.
Precisely. It learns to score translations based on perceived quality. Then the LLM you want to improve, that becomes your policy model in the reinforcement learning framework. You then fine-tune this LLM, the policy model, to generate translations to get the highest possible score from that reward model you just trained. So it's learning to produce text that the reward model thinks a human would find high quality.
Uh-huh.
There's some concrete work here, like Sue and colleagues in 2024, they built a big preference data set using multilingual books and then applied RLHF to fine-tune Lame 2 specifically for translation, optimizing directly against that learned reward signal.
That makes a lot of sense intuitively, aligning the model's output with what we think is good quality. But RLHF, it's also kind of notorious for being complex to implement, isn't it? There's a lot going on under the hood.
Oh, absolutely. That's one of its biggest drawbacks, frankly. The sheer number of moving parts is, significant. You need the reward model itself. You need the policy model that you're actually fine-tuning. You usually need a reference policy. Too often, the original pre-trained model, which helps prevent the model from forgetting everything it knew before, kind of a regularization step.
Mm.
And sometimes, you even need a value model as part of the RL algorithm.
Wow, yeah.
Managing and training all those components together, it dramatically increases both the memory requirements, these models are huge to begin with, and the overall computational cost of the training process. It's definitely resource intensive.
And I seem to remember reading about potential issues with stability, too. Like, getting the training to converge reliably can be tricky.
Yes, that's another major concern. Because you're training the reward model and the policy model somewhat separately, there's always this risk that the policy model learns to kind of game the reward model. It might find loopholes or exploit imperfections in the reward model to get high scores without actually generating translations that humans would genuinely prefer. This can lead to less robust models or sometimes even weird, undesirable outputs.
Okay, so given those complexities, the multiple models, the computational costs, the stability concerns, the motivation to find simpler, more direct alternatives seems pretty strong.
Absolutely. And that leads us straight to the motivation behind methods like direct preference optimization, DPO, and also SLIC. These techniques were developed specifically to try and elegantly bypass a lot of that RLHF complexity.
How do they do that? They still aim for the same goal, right? Aligning with preferences.
Correct. The goal is the same. Fine-tune the LLM using preference data, where you have pairs of preferred YW and dispreferred YL translations for a given source, X. But instead of the whole RL loop with a separate reward model, DPO and similar methods use some clever mathematical insights. They show you can actually formulate a direct loss function based on these preference pairs. You can essentially derive a closed-form expression that relates the model's probabilities for the preferred and dispreferred outputs to the implicit reward signal. And this loss function can then be optimized using standard techniques like gradient descent.
Ah, so it cuts out the middleman, the separate reward model step, and the complex RL training loop.
Exactly. It finds a way to directly optimize the policy based on the preference data itself. This has been shown to significantly reduce the computational complexity compared to RLHF, while still achieving really strong performance, particularly in machine translation, some recent work has demonstrated.
Okay, this is great background. And now here's where we get right to the heart of the CRPO paper, because even with these more efficient methods like DPO, there's still a really fundamental challenge, isn't there? And that's the data itself.
This is absolutely critical. The quality and, maybe even more importantly, the informativeness of the preference data you feed into DPO or SLAC is hugely important. We've seen this highlighted again and again, especially with major recent model releases. Think LAME3, for instance. A massive part of their reported success came down to incredibly careful, rigorous data curation. This involved really sophisticated processes for filtering preference data sets, removing low-quality pairs, identifying and maybe upweighting difficult examples, dealing with redundancy. It's a huge effort.
So it's not just about having preference data. It's about having good, carefully chosen, maybe even cleaned preference data that really makes the difference for these direct optimization methods.
Precisely. The data you use for preference optimization can be just as crucial, maybe even more crucial, than the specific optimization algorithm you choose. But, and this is a big but, that kind of exhaustive, often human-in-the-loop data cleaning and filtering, well, it's incredibly expensive, both computationally and in terms of human effort. It just doesn't scale very well, especially when you think about machine translation across potentially hundreds of language pairs. You can't manually curate everything perfectly.
Which naturally leads us to look for automatic ways to select the best data. The paper mentions some existing strategies here, like RSO and RSDPO. How do they generally work?
Right. Methods like RSO, that's rejection sampling optimization, and RSDPO, they primarily rely on the reward scores given to the candidate translations by a reward model. RSO uses a kind of statistical sampling technique based on those reward values. RSDPO is a bit more direct. It selects a preference pair if the difference in reward between the preferred and dispreferred candidate is bigger than some fixed threshold you set.
Okay, so they're focused mainly on the quality signal, the reward score.
Pretty much, yeah. They're definitely more efficient than manual cleaning, but their main focus is the translation quality as measured by the reward model.
So what key piece of information might these reward-focused methods be missing out on?
Well, they often overlook a really vital signal, which is the model's own state at the time of selection. Specifically, its confidence, or we could think of it as the likelihood it assigns to generating those specific translations itself. Knowing how probable the model thought the preferred translation was and how probable it thought the dispreferred one was, and crucially, the difference between those probabilities for that specific source sentence, that tells you a huge amount about how much the model actually stands to learn from that particular preference pair.
Ah, okay. So it's not just about the external judgment of quality, the reward score, but also about the internal state of the model, its own probabilities, that determines how useful a specific data point is going to be for training.
Exactly. Think about it like this. Suppose you have a preference pair where the reward model says, yep, U is clearly much better than AO. Okay, good reward difference. But what if the model you're training, the reference policy, was already super confident about generating Yule? Like it assigned a really high probability to Yule and a tiny probability to Yule.
Then maybe that pair isn't teaching the model much it doesn't already know.
Precisely. The model kind of gets it already for that pair. It doesn't offer much new information or signal a need for a big parameter update.
What if the reward model says Y is much better, but the model you're training was actually more likely to produce the bad one, U? Or maybe it was really uncertain, assigning similar probabilities to both.
Now that sounds like a prime learning opportunity, doesn't it?
Yeah.
That kind of pair highlights a significant misalignment between the model's current behavior, its likelihoods, and the desired outcome, indicated by the high reward difference. That gap, that misalignment, is exactly where the most effective learning can happen during preference optimization.
And this crucial piece, the model's confidence relative to the preference signal, that's what methods relying only on reward scores tend to miss.
That's exactly the insight that this CRPO paper leverages.
And that missing piece is what CRPO confidence reward-driven preference optimization aims to explicitly bring into the data selection process.
Yes, that's the core idea. It's a method designed specifically for selecting preference data by jointly considering both the reward scores, the quality signal, and the model's confidence or prediction likelihood for both the preferred and dispreferred candidates in a pair.
So instead of just finding pairs where one translation is clearly better than the other based on reward, they're trying to find pairs that are specifically challenging or informative given the current state of the model being trained.
Exactly that. They're trying to automatically pinpoint those teachable moments within the vast pool of potential preference data. They're looking for pairs where, yes, the quality difference is clear according to the reward model, but crucially, the model's own internal state, its probabilities, indicates that it's uncertain, confused, or maybe even biased towards the wrong answer for that specific input.
Okay.
The core hypothesis is that by focusing the fine-tuning effort on these specific, challenging, yet highly informative examples, you'll get more effective and more efficient learning.
And to quantify this idea of challenging yet informative, the paper proposes these two specific formulas for what they call a confidence reward score, or CR score.
Right. They developed two distinct scores, CR plus and CRA, designed to evaluate the potential learning value of any given preference pair by mathematically combining the reward signal and the model's likelihoods. Let's dive into how they actually derive these scores.
Okay. The paper says they derive these scores, CR plus and CRA, by analyzing the structure of the loss function used in DPO or CPO. What's the intuition there? Why look at the loss function to decide which data is good?
Well, the basic intuition is that data points which cause a large beneficial change in the loss function during training are likely the most informative ones for improving the model. If a data point leads to a big gradient update that pushes the model in the right direction, it was probably a valuable data point. So, by analyzing the mathematical form of the loss function, you can try to identify the characteristics of preference pairs, YWIWIL, that are likely to predict a large or particularly useful gradient update before you actually perform the update.
Okay, that makes sense. Let's break down the first one, CR plus, CR day. The paper says it's derived from thinking about the change in the loss function.
Yes. The idea for CR plus is that a preference pair is valuable if it prompts a significant beneficial shift in the model's behavior, its probability assignments during training. The paper approximates how much the loss function would change due to this specific pair. This change is mathematically related to the difference between the model's behavior before fine-tuning, which is captured by the reference policy, we call it PREF, and its desired behavior after fine-tuning, which they approximate as a policy that correctly and strongly favors the high-reward translation way of B.
So they're essentially trying to estimate how much the model's internal probability distribution needs to shift for this particular pair in order to align with the preference signal.
That's a great way to put it, yes. And the formal definition they arrive at for the CR plus score, it's in equation 7 in the paper, basically combines two main parts. The first part is a reward-based term. It looks like KRXYW, RXYL. Here, R is the reward score, X is the source sentence, YW is the preferred translation, IL is the dispreferred one, and K is just a hyperparameter. Scaling factor we'll come back to. This term directly captures the quality difference. A bigger positive value here means YW is judged as much better than DL by the reward model.
Okay, that's pretty standard acknowledging the quality gap. What's the second, more novel component?
The second component is the confidence or likelihood term. It's defined as log pref YWX. This measures the difference in the log probability assigned by the reference policy, pref, so the model before fine-tuning, to generating the dispreferred sentence YW given the source X.
Okay, let me just pause and make absolutely sure I've got that confidence term right. If log pref is larger than log pref, that means the original model, pref, assigned a higher probability to it, was sort of more confident in generating the worst translation by pref, AOWL, compared to the better one, YW. Is that the correct reading?
That is exactly correct, yes.
Yeah.
A large positive value for that whole term, log pref, signifies that the reference policy was substantially more likely to produce the bad translation than the good one. It was confused in the wrong direction, so to speak.
Got it. Okay. And you mentioned earlier that these two terms in the CR plus score, the reward term and this confidence term, they kind of conflict.
Yes, they do, in a sense. Look at how they're added together to make CR plus press. The reward term KRXYWRX, the while, becomes large and positive when the reward difference is large, i.e. YW is much better than Gilio. The confidence term log pref WX also contributes positively to CR plus when pref was more likely to generate DELU than YNAC.
So CR plus gets a high score when the reward difference clearly says me is better, and simultaneously the model's initial state, pref, was actually more confident about producing the worse option IL.
Precisely. This structure means CR Plus is specifically designed to prioritize those pairs where you have a strong quality signal from the reward model, a clear preference for he, but the model's initial state, pref, was poorly aligned with that signal. It was surprisingly likely to generate the bad option relative to the good one. Selecting these pairs basically forces the model to make a significant adjustment to its internal probabilities to align with the reward signal, hopefully leading to a large and impactful learning step during fine-tuning.
That's quite elegant, actually. It's deliberately seeking out the instances where the model is most wrong according to the external feedback and focusing the training effort there. And that K value is the knob you turn to balance how much you care about the size of the reward gap versus the size of the policy's misalignment.
Exactly. K is a hyperparameter that helps manage the potentially different scales or magnitudes between the reward score differences and the log likelihood differences. It also implicitly weights the relative importance of the quality gap versus the degree of policy misalignment in the selection process.
All right, that's CR plus, derived from analyzing the potential change in the loss. How does the second score, CR array, work? It's derived from analyzing the value of the loss function itself.
Right. For CRI, the intuition is slightly different. It's based on the idea that preference pairs which result in a high loss value, especially early in training, are likely the ones that the model hasn't yet learned effectively from. A high loss suggests the information in that pair hasn't been sufficiently incorporated. Now, a slight technical detail. The standard DPO loss function actually has a constant value at the very beginning of training, when the fine-tuning policy is identical to the reference policy. So to get around this and still use the loss value intuition, the paper actually uses a generalized CPO, contrastive preference optimization, loss formulation for the derivation of CRA. This allows them to identify data points that inherently correspond to a high informative loss value right from the start.
Okay, and what's the final formula for CRA?
CRA is defined quite simply as the product of two terms, as shown in their equation 11. The first term is, once again, the reward difference, RXYW, RXYLL. Just like before, this captures the quality gap between the preferred and dispreferred translations.
And the second term, is it the same confidence term?
Yes, it's exactly the same confidence term we saw in CR plus .freswex. Pref. Again, this captures how much more likely the reference policy fref was to generate the dispreferred ul compared to the preferred y.
So Ferrari is literally just the reward difference multiplied by that specific policy confidence difference term.
Correct. It's CRAA RX YW RX Y and X. Log fref YX. Now think about what makes this product large and positive. You need both terms to be positive and ideally large. The reward difference pref wag needs to be significantly positive, meaning log is clearly better than LO. And the confidence term log pref needs to be significantly positive, meaning Fref was much more confident in the bad translation IL than the good one YLA.
I see. So unlike CR plus VE, where the two conflicting terms are added together, in CR they're multiplied. Both conditions a clear quality gap, and the policy being more confident in the wrong one need to be met strongly for the score to be high.
Exactly. This multiplicative structure provides a kind of natural balancing between the two factors. If the reward difference is small, the CRE score will be small, regardless of the confidence term. Similarly, if the policy was already pretty confident in the preferred option, making the confidence term negative or close to zero, the CRE score will also be low or negative, marking that pair as less informative.
Interesting. Does that mean CRE might be less sensitive to needing that K hyperparameter tuning compared to CR plus plus, since the multiplication handles some of the balancing?
That's a possibility the paper hints at, yeah.
Yeah.
The multiplication might inherently handle some of the scale differences, potentially making it less reliant on careful tuning of a scaling factor like K, although they still use K in the CR plus formulation specifically for balancing.
Okay, so stepping back, both CR plus and CRA offer these quantitative ways to estimate how learnable or informative a potential preference pair is. And they do this by looking beyond just the quality difference, reward, to also incorporate how much the model's own current state needs to be corrected relative to that quality signal, confidence likelihood.
Precisely. They provide a principled, systematic method to move beyond just selecting pairs with the biggest reward gap or sampling based on reward. Instead, they identify and prioritize the pairs where the model is currently most uncertain or confused or outright incorrect according to the reward signal. The goal is to maximize the learning impact of each data point selected for fine-tuning.
It really shifts the perspective, doesn't it, from just what does good data look like to which data, even if maybe not perfect, is most useful for improving this specific model right now.
That's a key distinction, yes. It's about selecting for maximum learning potential given the current model state.
All right, so we understand the logic behind the CR scores. How does the actual CRPO algorithm use these scores to select the data in practice? What's the step-by-step process?
Yeah, the paper lays this out quite clearly in Algorithm 1 in their appendix. It details the procedure they use to select exactly one preferred-dispreferred pair, YWIIL, for each source sentence X in their training pool. That selected pair then becomes a single data point for the subsequent DPO fine-tuning stage.
Okay, walk us through it. How does it start for a given source sentence X?
First, for that source sentence X, the algorithm needs some candidate translations to choose from. So it starts by sampling a fixed number of candidate translations, let's say M candidates. In their experiments, they used M64. These candidates were sampled from a pre-trained ALMA7B model. Using the same model you plan to fine-tune, or a close relative, to generate the candidates is important. It helps ensure the candidates are sort of in distribution and relevant to the model's capabilities.
Right, so you generate, say, 64 possible translations for the source sentence. What's next?
For each of those 64 candidates, they calculate two things. One, its reward score, using their pre-trained reward model. They actually average scores from two common models. Two, its generation likelihood, specifically the log probability, log pref, under the reference policy that's the initial model state before any DPO fine-tuning begins.
Okay, so for every source sentence, you've got 64 options, each with a quality score, reward, and a how likely was the original model to say this score, log pref.
Exactly. Now comes a really important step to anchor the process to quality. From those 64 candidates, they first identify and select the single sentence that has the absolute highest reward score. The sentence is designated as the preferred sentence, UI can of go. For this source sentence, guaranteed.
So the good example in the pair is always chosen to be the best one available according to the reward model.
Yes. This ensures a baseline level of quality for the positive example in the pair. It aligns with practices seen in other large-scale data refinement efforts, like for Lemma 3, where ensuring the quality of the chosen examples is paramount.
Makes sense. You want your target to be genuinely good. What happens then?
Then, the algorithm iterates through all the other M1 candidates, the 63 remaining ones in this case. Each of these is considered as a potential dispreferred sentence, ecumedal, which confirm a pair with the heel we just selected. Now, here comes the really crucial filtering step that uses the policy confidence information. The algorithm only considers pairs, AWIAL, where the log likelihood of the potential dispreferred sentence YAL, where the log likelihood of the potential dispreferred sentence Y, according to the reference policy pref. So the condition is log freshus YGJ the IPX.
Wait, hang on, let me process that again. They are deliberately keeping only those pairs where the original model FREF was more likely to generate the worst translation than it was to generate the best translation, YAW. That still feels counterintuitive at first glance. It does, but it's precisely the core of the CRPO selection strategy. Remember that confidence term we discussed? Log, Preval, Prevalent, Proix? This filtering step explicitly ensures that this term is positive. By applying this filter, they are isolating exactly those candidate pairs where the policy's internal probabilities are demonstrably misaligned with the external reward signal. They're finding cases where the model was surprisingly more likely to produce the lower quality output compared to the high quality one.
Okay.
These are precisely the pairs that reveal the model's current weaknesses or points of confusion. They represent the biggest opportunities for learning and correction during the fine-tuning process.
Okay, I think I'm getting it now. So they find the absolute best translation by reward, IW. Then they look at all the other worst translations,
Yeah.
LVASEL. From those, they specifically pick out the ones that the model was perhaps surprisingly more confident about generating compared to the best one, IW. You've got it. That's the essence of the selection filter. So among all the candidate sentences LEL that pass this filter, the ones that form pairs, YWA, LEL, satisfying log, pre, LBX, the algorithm then calculates the CR score using either the CR plus or CR formula for each of these qualifying pairs. And finally, from this filtered set of potential dispreferred candidates AALL, it selects the single one that results in the pair, IOVOVOEL, yielding the maximum CR score.
Wow.
That single pair, the one with the highest CR score among those meeting the misalignment criterion, becomes the final chosen data point for DPO fine-tuning for that specific source sentence X.
Okay, so let me try to recap the whole selection logic. For each input sentence, generate a bunch of possible translations. Find the best one based on quality reward score, that's your good example. Then look at all the worst options. Filter those down to only the ones the original model was actually more likely to produce than the good one. And from that filtered set, pick the single pair that maximizes this combined confidence reward score, CR score, indicating the biggest, most informative misalignment for the model to learn from.
That's an excellent summary. You've nailed the process. And this entire procedure is repeated for every single source sentence in your initial training pool, creating the final curated preference data set that gets fed into the DPO fine-tuning stage.
It definitely sounds like a much smarter way to automatically identify the most potent training examples compared to just looking at reward scores. How do they go about testing whether this theoretically nice strategy actually translates into better performance in practice?
Right. The proof is in the pudding, as they say. They conducted a series of empirical evaluations focused squarely on the machine translation task. They compared the performance of models fine-tuned using data selected by their CRPO method against models fine-tuned using data selected by several baseline methods.
What were the specifics of the data they used to generate all these preference pairs for training? Where did the source sentences come from?
The source sentences themselves were drawn from the Flores 200 dataset. This is a pretty standard, large-scale, multilingual benchmark dataset often used in MT research. They focused on 10 specific translation directions involving English, paired with Chinese, German, Czech, Icelandic, and Russian. So English to Chinese, Chinese to English, etc. This gave them a total of about 24,314 unique source sentences across these 10 directions. The number varied a bit per direction, like around 3,000 for English, Chinese, German pairs, and 2,000 for the others.
Okay, and for each of those 24,000 source sentences, they needed candidate translations to form the potential preference pairs. You mentioned they sampled 64 candidates.
Yes, 64 candidates per source sentence. That resulted in a large initial pool of roughly 780,000 candidate translations in total, 24,314.64. And as we noted before, these candidates were sampled specifically from a pre-trained ALME 7B model, which itself has connections to Flores 200.
Yeah.
This was a deliberate choice to try and minimize distribution shift. You want the candidates to be somewhat representative of what the model you're fine-tuning might generate?
Any particular sampling settings, like temperature?
Yeah, pretty standard settings.
Yeah.
Temperature set to 0.9 and top also set to 0.9 during sampling.
And how did they get the crucial reward scores for all these 780,000 candidates? What reward models did they use?
They used two different strong, large Comet-based reward models, specifically XComet XL and WMT23 Comet Kiwi Day XL. Both are around 3.5 billion parameters. To get a more stable and hopefully robust quality estimate for each candidate, They actually averaged the scores produced by these two Comet models.
Okay, that makes sense for the training data generation. What about evaluating the final fine-tuned models? What test sets did they use to measure performance?
They use standard, publicly available WMT workshop on machine translation test sets, specifically WMT21 data for the English-Icelandic directions and WMT22 data for the other 8 directions, involving Chinese, German, Czech, Russian. This gave them a diverse evaluation set comprising about 70,471 translation pairs in total, allowing them to assess performance across all the different language pairs they trained on.
What actual models did they apply CRPO to? Did they stick to just one type of LLM architecture?
No, and this is important for showing generality. They evaluated CRPO on 2 distinct architectures. Their primary model was LMA7B. This is a decoder-only LLM, similar in style to models like GPT or Llama. They started from a specific pre-trained checkpoint called LMA7B pre-trained LoRa, and they fine-tuned it using LoRa low-rank adaptation. This is a very popular parameter-efficient fine-tuning technique where you only train a small number of additional parameters, keeping the bulk of the large model frozen. For LMA7B, they used a LoRa rank of 16, which meant they only had to train about 7.7 million extra parameters on top of the base 7 billion.
Okay, so a decoder-only model. What was the second architecture?
To demonstrate versatility, they also applied CRPO to NLLB 1.3b. This is an encoder-decoder model developed by Meta, specifically designed for massively multilingual translation. They started from the publicly available Facebook NLB 200-1.3b checkpoint and fine-tuned it, adding about 27.7 million trainable parameters in this case. This test was crucial to show that the CRPO data selection approach isn't just limited to decoder-only models like ALMA.
Good. Showing it works on both types is definitely valuable. Can you give us some specifics on the fine-tuning process itself? What objective hyperparameters?
Sure. They use the DPO, direct preference optimization, objective for the fine-tuning stage, using the preference pairs selected by CRPO. Key hyperparameters included beta, which controls the strength of the DPO regularization term, was set to 0.1. They used a batch size of 16, a learning rate of 1E4, 0.00001, and a learning rate warm-up phase covering the first 1% of training steps. Importantly, the fine-tuning was done for just one epoch over the selected preference data, and they used a maximum sequence length of 512 tokens.
Okay. And what about that K hyperparameter needed for the CR plus score calculation? Did they have to tune that carefully for each model or language pair?
That's a good practical question. For CR plus N, they actually set K to a single value of 50 for both the LMA7B and NLLB 1.3b models, and they used this same value across all 10 translation directions. The paper mentions this value 50 was chosen empirically to help bridge the magnitude difference between the reward scores and the log likelihood differences, making them comparable when added together in the CR plus formula. Using a single K value simplifies deployment significantly compared to needing different Ks for every situation.
Any other notable training details, like efficiency tricks or prompt formats?
Yeah, a few more details. They use DeepSpeed, a library for optimizing large model training to improve efficiency. For the LMA7B model, the decoder-only one, they used a specific prompt format that looked like. Translate this from source language to target language, source sentence, target language. They made sure to exclude these prompt tokens when calculating the loss during training, so the model was only penalized based on the generated translation itself. They also mentioned adding an SFT, supervised fine-tuning loss term, alongside the DPO loss, with a weight of 1. This is a fairly common practice in DPO training, adding a term that encourages the model to simply mimic the preferred translation, YWO, can help stabilize training and maintain the model's core generation capabilities while it also learns the preference.
Okay, got it. And finally, how did they measure success? What metrics did they use to judge the quality of the translations produced by the fine-tuned models?
They relied on several standard and widely accepted automatic metrics for machine translation quality. Primarily, they used different variants of the COMET metric. COMET is a neural metric that's known to correlate well with human judgments. They reported scores for KW22, COMET22, XCOMET, and KiwiXL, slightly different versions trained on different data or with different architectures. Now, since they use COMET models as part of their reward scoring during data selection, there's always a slight concern. Are you just getting good COMET scores at evaluation time because you optimized for something similar?
Right, teaching to the test, essentially.
Exactly. So, to address that potential concern and ensure the gains were real, they also included BLERT20 as an evaluation metric. BLERT is another learned metric based on contextual embeddings, but it's developed independently from COMET. Showing improvement on BLERT helps confirm the gains aren't just an artifact of using COMET for both reward and evaluation.
That's smart. Okay, we have the setup. What other data selection or fine-tuning strategies did they compare CRPO against? Who are the baselines?
They had a pretty comprehensive set of baselines to compare against, which is good scientific practice. These included, first, a simple QE fine-tuning baseline. Here, for each source sentence, they just selected the single candidate translation that got the highest reward score. QE stands for quality estimation, another term for reward score here. Then they fine-tuned the model using standard supervised fine-tuning, SFT, on these source best translation pairs, no preference pairs involved. Then they include an RSO, rejection sampling optimization, which selects pairs based on statistical sampling weighted by reward. And RSDPO, which selects pairs using DPO, but the selection criteria is simply that the reward difference between preferred and dispreferred exceeds a certain threshold. They tested a few different threshold values denoted. They also compared against methods using MBR score. MBR stands for minimum Bayes risk, often used in decoding. Here they use BLERT 20 scores to select pairs, either the best versus the worst candidate, MBR-BW, or the best versus middle versus worst, MBR-BMW. A very interesting baseline was the triplet dataset. This involved using a publicly available preference dataset released as part of a previous paper on CPO, contrastive preference optimization, by Zhu et al. This dataset was built using translations from various sources like GPT-4, humans, and another model. Comparing against this test whether CRPO selection logic applied to their sampled candidates is better than just using a potentially high-quality but differently sourced external preference dataset. And finally, as an upper bound reference, they included the goal reference score, essentially, the score the human reference translations from the test set achieve on the evaluation metrics. No system is expected to beat this.
Wow, okay, that's a really solid set of comparisons covering different philosophies of data selection and fine-tuning. Let's finally get to the results. Table 1 in the paper shows the average performance across all metrics for the LMA 7B model. What's the headline news there?
The headline news from Table 1 is pretty striking. Across the board, looking at the average scores over all the different common metrics, CRPO Plus achieves the best performance. And right behind it, CRPO-A is the second best.
So the two methods that explicitly incorporate the model's confidence signal into the data selection significantly outperform all the other methods, including those that focus primarily on reward scores like RSO, RSDPO, and the MBR strategies.
Exactly. That's the key empirical takeaway. It provides strong evidence supporting their core hypothesis that adding this confidence component to the reward signal leads to selecting more effective training data, resulting in tangibly better translation performance after DPO fine-tuning.
That's quite convincing. What about the triplet dataset baseline? How did that perform? It came from potentially strong sources like GPT-4.
Interestingly, the triplet dataset baseline actually performed worse, on average, than both RSO and the CRPO methods in their experiments on LMA7B. The paper offers a plausible explanation for this: potential distribution shift. The triplet dataset was created using different models and possibly different source data than the LMA7B model they were fine-tuning. Using preference data that's out of distribution for the model being trained can sometimes be less effective than using data derived from the model's own candidate space, even if the external data seems high quality in isolation. CRPO, by selecting from candidates sampled from LMA7B itself, avoids this particular issue.
That makes sense. And what about RSDPO? Its performance seemed a bit variable in the table, depending on the threshold used for the reward difference.
Yes, that's another point the paper highlights. The performance of RSDPO was indeed quite sensitive to the choice of the reward difference threshold. They note that finding a single optimal e-value that worked well across all 10 different translation directions was challenging. Why? Because the inherent difficulty for the policy model to distinguish between preferred and dispreferred translations can vary a lot depending on the language pair and the overall quality of the model for that pair. A threshold that's good for English-German might be too high or too low for English-Icelandic.
Right.
CRPO, on the other hand, while CR Plus does have the hyperparameter K, they found they could use a single value of K, K50, across all language directions in their experiments and still achieve consistently strong results. This practical aspect, not needing per-direction tuning, is a potential advantage.
You mentioned earlier they included results for individual language directions and also for the non-comment metric, BLERT, in the appendix. Did CRPO hold up well in those more detailed views?
Yes, and checking these appendix results is important for confirming the robustness of the findings. Appendix C.1 provides tables with detailed scores for each of the 10 individual translation directions. Looking through those, CRPO, usually CRPO Plus, performs best or is extremely competitive on almost every single direction. This demonstrates that its effectiveness isn't just an artifact of averaging or skewed towards only one or two language pairs. It seems generally beneficial. And Appendix C.2 shows the results using BLERT 20 as the evaluation metric. Even with BLERT, which is independent of the Comet reward models used during data selection, CRPO Plus and CRPO still come out on top, achieving the highest scores compared to the baselines.
Okay, that definitely addresses the teaching to the test concern
Right.
and boosts confidence in the generality of the improvement.
Exactly. It suggests that performance gains are real and not just an artifact of the evaluation setup.
And quickly, what about the results for the NLLB 1.3b model in Table 2? Did the CRPO advantage carry over to the decoder architecture as well?
Yes, it did. Table 2 shows the results for fine-tuning the NLLB 1.3b model. Again, CRPO Plus achieved better average performance across the metrics compared to the other data selection methods tested. This is a crucial result because it demonstrates the core principle behind CRPO, using both confidence and reward for data selection, isn't just something that works for decoder-only LLMs like LMA. It seems to generalize effectively to the very different architecture of encoder-decoder models like NLLB, which are also widely used for translation.
That's great to see. Showing versatility across architectures really strengthens their claims. Now, the paper also includes some visualizations, figures 2, 3, and 4, which try to give some intuition about why CRPO's selection strategy is different and effective. Can you unpack what those figures are showing?
Yeah, these visualizations are helpful for understanding the characteristics of the data that actually gets selected by CRPO versus the other methods. Figure 2, for example, shows some basic distributions, things like the reward scores and the log probabilities, log pref, for the entire pool of candidate sentences, and then for the subsets of preferred YW and dispreferred YL sentences selected by different methods. As you'd expect, selected YL sentences generally have higher rewards, and selected YL sentences have lower rewards. That's just confirming the reward models are working.
Right. But the more interesting part is how the policy likelihood log pref plays into the selection for the different methods, especially in Figure 4.
Exactly. Figure 4 is where you really see the difference. It plots characteristics of the selected pairs. What you observe for methods like RSDPO, RSO, and MBRBW is that they tend to select preferred sentences, YW at LW, that already have a higher generation likelihood, log pref, under the reference policy compared to the dispreferred sentences that paired with. Meaning that for the pairs these methods select, the model's initial state, pref, was already relatively good at distinguishing the preferred from the dispreferred option. It was already more likely to produce the good one than the bad one. The paper refers to these as being comparatively easy data points for the model to learn from the model's internal state wasn't strongly misaligned with the reward signal for these pairs.
Okay, so those methods pick pairs with a clear reward gap, but where the model kind of already leaned in the right direction anyway. How does CRPO look different in Figure 4?
Well, Figure 4C visualizes the distribution of the log likelihood difference, specifically log pref, log pref and stelix, for pairs selected by different methods. What stands out for CRPO Plus and CRPOA is that they're selecting pairs where this difference is predominantly negative.
A negative value for log pref preps light means?
It means that log pref preps is less than log pref likes. In the plain English, for the pairs selected by CRPO, the model's initial state pref was actually less confident in generating the preferred sentence me than it was in generating the dispreferred sentence me.
Ah, there it is visually. The plots confirm that CRPO is actively seeking out and selecting precisely those pairs where the model's own initial probability distribution is misaligned with the external quality judgment from the reward model. It's picking the examples where the model was surprisingly more likely to get it wrong relative to getting it right.
Exactly. The visualization confirms the algorithmic logic we discussed. This selection strategy deliberately focuses the fine-tuning process on the pairs that are most challenging or confusing for the policy in its current state, those where its internal understanding of the preference signal is weakest or pointing the wrong way. The hypothesis, supported by the results, is that targeting these specific points of weakness maximizes the learning potential and drives more significant performance improvements.
That visual really helps solidify the core technical contribution here. The paper also performed some ablation studies presented in Table 3. What did those aim to show?
Ablation studies are super important in research like this. They're designed to isolate the contribution of each specific component of a proposed method to make sure everything included is actually necessary and doing useful work. In Table 3, they essentially tested variations of their data selection strategy where they systematically removed either the reward component or the confidence likelihood component, or they used much simpler selection logic based on only one factor.
Like the min-max-R strategy listed there. What was that?
Min-max-R stands for minimizing maximizing reward. In this ablation, they selected the preferred, ray W, and dispreferred weight O, based solely on maximizing the reward difference, RRW, among all possible pairs from the 64 candidates. This effectively drops the policy confidence likelihood term from the CRPO selection logic.
Kind of the
Its performance was significantly worse than both CRPO Plus and CRPOA. This provides strong empirical evidence that the confidence term isn't just fancy math, it's genuinely necessary for achieving the performance gains seen with CRPO. Just maximizing reward difference isn't enough.
Okay. And what about the other ablations, like min-max P or min-max PO, which seem to focus more on the policy likelihood?
Right. Those strategies involve selecting pairs primarily based on likelihood differences, g.g. finding pairs where log for QOU was maximized, or other combinations that didn't strongly incorporate the reward signal, indicating actual sentence quality. Unsurprisingly, their performance was also substantially lower than CRPO. This demonstrates the flip side. Sentence quality, as measured by the reward model, is also a necessary component. You can't just pick pairs where the model was uncertain or confused. Those pairs also need to clearly represent a preferred outcome, high reward difference, according to an external quality measure.
So the ablation studies really nail it down. The power of CRPO comes from the synergy between considering sentence reward and the model's prediction likelihood together. You truly need both signals working in concert for effective preference data selection in this framework.
Precisely. They effectively prove, through empirical testing, the necessity of their core technical innovation, which is combining these two aspects in a principled, score-based way. They also included a simple top scores baseline in the ablations, which just involves selecting top K candidates based on reward score alone for SFT. That performed even worse than RSO, suggesting that simple reward ranking might lack diversity or fail to capture the kind of informative contrast needed for preference learning.
Very thorough. The paper also tucked away a couple of other interesting experiments in the appendix. One looked at mixing CRPO's sample data with external data.
Yes, that was in Table 7. An interesting question is whether CRPO's selection logic is only good for picking the best pairs from candidates generated by the model itself, or if it can also effectively curate data from other sources. To test this, they created a mixed pool of candidates by combining their 64 sampled candidates per source sentence with the candidates available in that external triplet dataset from Seward et al. Then, they applied the CRPO selection algorithm, both CR plus and CRE versions, denoted with a star like CRPO plus, to this larger mixed pool.
And what happened?
The models trained on data selected by CRPO from this mixed pool actually performed slightly better than both the model trained using CRPO only on the sampled candidates and the model trained using the triplet dataset alone.
Huh. What does that suggest technically?
It suggests that the CRPO selection logic is quite robust. It's effective not just for refining candidates generated by the target model, but also for identifying the most informative pairs, even when drawing from a diverse pool of external data, which might contain candidates of potentially higher absolute quality overall. CRPO seems capable of picking out the pairs that offer the best learning opportunity for the current model state, regardless of where those candidate translations originated, by applying its joint confidence reward criteria.
That's a strong indicator of its potential usefulness for curating diverse data sources. They also tested using the CRPO selected data to fine-tune with CPO instead of DPO, right? What was that about?
Right, that's in Table 8. CPO, contrastive preference optimization, is another preference learning objective, very similar to DPO, but it technically drops the explicit KL divergence term that DPO uses to penalize the policy for moving too far away from the reference policy, pref. So they took the data selected by CRPO and fine-tuned the models using the CPO loss instead of the DPO loss. They found that fine-tuning with CPO on CRPO selected data still significantly outperformed fine-tuning on the external triplet data with CPO. So CRPO's data selection benefit holds up even if you switch the optimization objective slightly.
But did CPO offer any advantage over DPO when using the CRPO selected data?
Interestingly, no. Fine-tuning the CRPO selected data with CPO did not lead to better performance than fine-tuning the same CRPO selected data with DPO. In fact, DPO performed slightly better or was on par.
Any speculation why removing the KL term didn't help further, given the supposedly high-quality selected data?
The paper offers a plausible hypothesis. They suggest that the data selected by CRPO is already so effective at pushing the model towards high-reward translations, specifically by targeting those misaligned, high-learning potential areas, that the explicit regularization provided by DPO's KL term might not be strictly necessary. or perhaps even slightly limits the maximum performance gain achievable within that single epoch of training. In other words, the signal from the CRPO selected data might be strong and targeted enough that the model doesn't need the KL term to prevent it from going off the rails, and removing it, as CPO does, doesn't unlock further gains because the data itself is already driving such effective learning.
Fascinating. It really underscores how much the data selection strategy itself is doing the heavy lifting here. Did the paper identify any limitations or potential weaknesses of their current CRPO algorithm?
Yes, they do acknowledge a technical limitation in the current formulation presented in Algorithm 1. As we discussed, the algorithm selects only the single pair, YWYYL, that yields the absolute maximum CR score for each source sentence X.
And the potential issue with only picking the single top pair.
The issue is that there might be other candidate pairs for that same source sentence X that also have very high CR scores, maybe slightly lower than the absolute maximum, but still representing significant and valuable learning opportunities, i.e., clear reward gap and high policy misalignment. By only taking the single best pair, the current algorithm might be discarding other potentially high-quality informative training data points.
So it might be leaving some useful learning signal on the table, potentially making the data usage slightly less efficient than it could be.
Exactly. It's a trade-off between simplicity, picking just one pair, and potentially maximizing data utilization. They do mention potential technical solutions or directions for future work to address this. For instance, instead of taking only the max score pair, one could use a preset threshold for the CR score and include all pairs that exceed it. Or perhaps analyze the distribution of CR scores for the filtered candidates for a given source sentence and select a small batch, say top 3 or top 5, of the most informative pairs, not just the single best one.
That definitely seems like a logical next step for potentially optimizing the data efficiency even further.
It does, yeah.
Okay, so let's try and bring this deep dive into the CRPO paper together. Stepping back and looking at the whole thing, what's the big picture technical takeaway for you?
For me, the main takeaway is a reinforcement of a trend we're seeing more broadly. Simply having preference data, or even just using reward models to score candidates, isn't necessarily the endpoint for optimally fine-tuning these incredibly powerful large language models, especially for complex, generative tasks like machine translation. The key technical innovation demonstrated by CRPO is showing that intelligently selecting which preference data to actually train on by critically considering not just the external measure of quality reward, but also the model's internal state, its confidence or likelihood for those outputs, is crucial for pushing performance boundaries and doing so efficiently.
Right. It's about moving beyond just finding good data to finding the data that specifically targets the areas where the model is currently most uncertain or confused or just plain wrong relative to the desired outcome.
Precisely that. And the experimental results they presented, showing consistent gains on both decoder-only, ALMA7B, and encoder-decoder, NLB 1.3b models, compared to strong baselines that rely solely on reward, provide compelling empirical validation for this approach. It points towards a more sophisticated model-aware strategy for data curation in the context of preference learning.
And the ablation studies really hammered home that this combination of confidence and reward isn't just a nice to have. It appears to be the necessary technical core driving their improved results.
Absolutely. They systematically showed that removing other component significantly degrades performance, highlighting the importance of their joint consideration.
So, thinking about the broader implications, what does this all mean for how we approach training large models on these complex generation tasks? We've seen here how focusing the fine-tuning effort not just on data points that score well externally, but specifically on those points where the model struggles to distinguish between good and bad, how that can yield significant performance gains.
Yeah, I think this core technical idea, this method of identifying hard negatives or maybe confusing positives based on a combination of the desired outcome, reward, and the current model state, confidence probabilities, feels like it should be broadly applicable. You can easily imagine applying a similar philosophy to improve other generation tasks where preference optimization is becoming common. Think about text summarization or dialogue systems and maybe even code generation, anywhere you're trying to align a powerful generative model with complex, nuanced human preferences. This strategy of focusing on the model's points of maximum uncertainty or error could potentially make the training process more effective and perhaps more data efficient.
It certainly opens up some really interesting avenues for future research and development. It makes you wonder, and here's maybe a final provocative thought for you and for our listeners. Could we even take this a step further? Could a more dynamic approach to data selection work? Imagine an algorithm where the balance or the specific criteria for selecting data Maybe the relative weighting of reward versus confidence or the type of misalignment it looks for actually shifts over the course of training. As the model gets better, maybe it needs to focus on different kinds of challenging examples.
Ooh, that's a really interesting thought. An adaptive selection strategy. Yeah, you could hypothesize that as the policy improves and becomes more confident in areas where it was previously uncertain, the definition of what constitutes an informative or challenging pair might need to evolve. Maybe early in training, you focus on pairs with huge reward gaps where the policy is wildly wrong, like CRPO does now. But later, as the model gets better, maybe the selection strategy needs to adapt to seek out pairs with more subtle quality differences, or cases where the model is just slightly miscalibrated, to really refine its understanding of nuanced preferences. That's a fascinating direction for future work.
Definitely something to ponder. Well, this has been a fantastic deep dive into the technical nuts and bolts of CRPO and the importance of smart data selection for machine translation. Thanks so much for unpacking that with us.
My pleasure. It was great digging into the details.
And thanks to all of you for listening. Join us next time on The Deep Dive.